Thank you very much. I thank Stefan for the nice invitation. I thank you for being here. I would like to tell you that please, if you have any questions or any comments along the talk, so please just raise your hand, and this makes everything more interactive and more dynamics now. Okay, so the idea is just to give a flavor about metasurfaces, and since the audience is very diversified with many different backgrounds, so I would try to tell you a story, and this is what I would like to approach. I would just tell you what are metasurfaces, show you how they can be applied and used, and then I will bring this, the metasurfaces to the field of tunability. So we would like to have dynamic metasurfaces, and one possibility of doing this is to use phase change materials. And in our case, we will focus on vanadium dioxide. And then I will just show you how can we tune the optical properties of such metasurfaces in the visible range, and focusing on the optical properties of single vanadium dioxide VO2 nanodiscs, and then how can we change the properties of disks when we put them together in an array, so making a metasurface from them. And then I will show you how can you switch these optical properties of such metasurfaces, and how can we use this for something nice. Okay, so metasurfaces, they are so artificial structures that you have to make. You don't find them in nature, and they are made by an array of smaller elements, and smaller than typically the wavelength that you're using. And the metasurfaces allow us to fully control the properties of light by, in the end, controlling the phase of the incident light at every point in space. So we are familiar with Maxwell's equations. Maxwell's equations govern the propagation of electromagnetic waves, and this propagation is very boring until the wave finds an interface. So it's everything about the surface, right? And this is why metasurfaces are so important in modern optics, because it's there where everything happens. So if you are able to manipulate the characteristics, the properties of light at an interface, then you are playing a hard game. Okay, one goal of present modern nanophotonics is to realize what people call flat optics. So it's to try to eliminate any kind of bulky elements and reduce this a lot, helping, for example, the integration in more complex circuits and so on. So this is slowly get to a reality. So if you can imagine which kind of lenses you have in your mobile phones, which allow you to have a very nice field of view and so on, and it's a tiny, tiny, tiny element, right? So in my mobile phone, I have a lens for making very strong zooms, and these are tiny lenses that must have a very short focus, and it's not possible to use in such a device as bulky lenses. And then the sky is the limit. You can think about making devices, holograms, images, switches with superior properties than what we have presently. And I would like to mention some examples about this. Here we can see, for example, an electronic microscope image of a metasurfaces, which is composed by these silicon disks, right? So this operates in the near infrared. You see that the size of these disks is about 500 nanometers. They are very close to each other, right? And with such a disks, we may achieve interesting properties. Like, for example, each one of these disks supports so-called Mie resonances, right? So in these Mie resonances, they may have a typical electric dipole characteristic or a magnetic dipole characteristic. And there is a known result in this area, which is the so-called Kercher condition, which tells us that when you have the electric dipole and the magnetic dipole contributing with the same amplitude, and we see here that this happens at 1,300 nanometers or so, this metasurface may act as a strongly directional scatterer. So this is nothing special, so this comes from the scattering theory, but this is an important thing because many times you want to shine light on the surface, you want to have a large transmittance, but also sometimes you want to have a large reflectance. And there is also another similar condition to this which makes the metasurface strongly reflecting. So this is one application. Another important application is using a plasmonic metasurface. So you have gold nanorods with sizes typically of 300 nanometers and so on a substrate, right? And they have been, the orientation of these rods was projected in order to allow you to have a very large diffraction efficiency in an holographic application when you shine this metasurface with circularly polarized light, and you can convert a huge amount of the incoming energy to the produced hologram, right? And in a broadband way also. So you see that you have a high efficiency over 200 nanometers or so. And here we see two holograms produced by this metasurface, so this reflection hologram. And we see here that the quality at 633 nanometers is not as good as 780 nanometers, but you can also produce holograms with broadband characteristics using a metasurface, a plasmonic metasurface. Another important use for these metasurfaces is converters, polarization converters or polarization controllers. In this case, this metasurface is composed by silicon nanopillars with a given orientation, the height and the orientation. This brings a kind of anisotropy at each point in space. And with this, you can, for example, control the incident polarization. So here we have incident linear polarization. And after the metasurface, we have, in this case here, a circular polarized light. And this kind of structure allows you to have this property over a broad band wavelength range. So this would substitute, for example, broadband wave plates, which are bulky elements, by some structure which is only half a micron high. So this is also a huge flattening in the optics of the setup. Another very nice application is the multiplexed holography. By the way, the first author of this paper is Dr. Howard Ren, who is working here in this institute. So what he did, it was something fantastic. This paper uses also direct laser writing. So a polymer is used on a substrate, and via two photon polymerization, you can fabricate these pillars, which, depending on their orientation on the substrate and the height, allow us to control the amplitude and the phase of the light at each point of the metasurface. And with this, depending on how you shine light on this metasurface, you can produce a hologram. So if you want now to make dynamic holograms, so if you want to project a movie, a holographic movie, you need to shine different kinds of light on this metasurface. Up to today, what people did is using light with different circular polarizations, so the spin degree of freedom in the polarization of light, but you have only 3 possible channels with this. The important contribution of this paper is that it started to use now the orbital angular momentum of light, so wave fronts with twisting pointing vector or with topological charge, which is practically an unbounded degree of freedom of light. So you can have a beam of light with any kind of topological charge. And then in this case, topological charges between -50 and +50 were used to produce a hologram with 100 frames at a rate of 25 frames per second. So you see the hologram, so a movie playing in space. And this is also nice because this kind of approach allows you to also project a second hologram displaced in the Fourier space, and this in the end allows you also to project 3D holograms. So this is a very important work in the area of holography and exploring also the properties of the metasurfaces. Other kinds of devices are biosensors with enhanced sensitivity, and in this case these silicon metasurfaces have been constructed, but they also bring another aspect to the problem, which is the following. These pair of tilted ellipses, they present what people call the quasi-bound continuous states in the continuum, and these are resonances that come from the interference between a continuum of states and discrete states. This means that these resonances also, they bring some enhancement of the electric field at given positions of this metamolecule here, indeed in this case a diatomic metamolecule, right? And one interesting thing is that you can tune these resonances to the middle infrared region of the spectrum, where many molecules, many important molecules have their infrared absorption fingerprints. These kind of metasurfaces allow, these structures also allow you to, depending on the scaling factor, so if you increase these metamolecules a little bit in size or decrease them, or if you change a little bit the angle between these two ellipses, you can also tune the resonance of this structure. This means that if now I have a metasurface, a pixelated metasurface, where each row presents a different, each row has a different scale factor, and each column has a different tilt angle, you can tune these resonances across a huge spectral range, where many molecules of biological interest or pharmacological interest have their fingerprints, the infrared absorption fingerprints. Nice. This means that you have this kind of structure, and now if these molecules just land there on this metasurface, which you see here, it's really very small, so 1.5 millimeters in size, what you get is something like this. In the regions of the spectrum where the molecule strongly absorbs, the pixel corresponding to this area will be a little bit darker than the others. This means that if you just take a picture, you shine light on this metasurface, and then you record, then you find out where are the regions of stronger or weaker reflection, you can say which kind of molecule landed there, right? So, and with also an enhanced sensitivity because of these resonances, which make the electric field at these wavelengths here stronger, and as a consequence, the molecules will absorb also stronger light at these wavelengths. Another important device came with a new vision of the optical metafibers. So in this case, this work intended to design an aberration-free metalens. So the idea is to get an ordinary single-mode optical fiber, right? And then if you just couple white light here, this metalens, which is just fabricated on a tower, which also is built at the end of this optical fiber, it's there just to allow the light to get a little bit broader so that you can illuminate the whole metasurface. All these wavelengths would be focused at the same position. So you produce an achromatic lens, which is flat. And then you can also imagine what's the importance of these things when you're imagine any kind of application in diagnosis, like so this device that you use to investigate your stomach, right? Because you get a sharp image in all colors you use, right? And in this case, also this direct laser writing has been done, right? Has been used in order to photopolymerize fluid polymer and construct these nanopillars, which again allow you to have the same focal position. Here is the axial focal position for different wavelengths, and here you see for each wavelength the position of the focus. So it's a very broad achromatic lens, also in the spirit of flat optics. Again, another application is in ultrafast light modulation and generation of new frequencies. So in this case, the metasurface was composed by gold discs that had a slit or a half a slit here in the middle. So for such structures, if you just make what is called white light spectroscopy, you see that there is a strong resonance. It's when you excite the dipole, the electric dipole of these charges here. So the extinction is larger at 800 nanometers for this polarization. But if you cross the polarization, you get a completely different response of this structure. And this is because in this case you not only excite the dipolar the oscillation of these charges, but also a quadrupolar, electric quadrupolar oscillation, and also a magnetic dipole is created here because you induce currents, and which makes this like an inductor, and also you generate a magnetic response. In any case, you can use these resonances, for example, in order to enhance the conversion efficiency of incident light. So if you have, for example, light at 1200 nanometers or so, they will feel a much enhanced local field, and then the conversion efficiency will be much larger. And this is what we show here. So these are the results resolved in time for some frequency generation or four-wave mixing, never mind. But you see that here the ultra-fast response of this structure with a very nice signal-to-noise level. And this is due to the resonances that are being exploited in such metasurfaces. Okay, so after having this seen and discussed these many different applications, possible applications of metasurfaces, the next natural step would be to incorporate any kind of tunability. So we would like to try to change the behavior of these metasurfaces while they're being used, right? And there are many different approaches that you can use to do this, and this depends on your application, right? For example, you can use incident light in order to change the transmission of such a metasurface. In this case, you send a probe, so you want to monitor the transmission of this probe. But whenever you have a pump, an ultra-fast pulse of light, you change the absorption properties of these meta-atom here. In this case, it's a two-photon absorption process, which makes the transmission change a lot in a very fast manner. So you can change the transmission of this metasurface in ultra-fast times, right? Another possibility of changing the properties of a metasurface is in a system like this, which is applying an external voltage. In this case, the metasurface was composed by concentric circles of tungsten disulfide, right, on a sapphire substrate. And when you apply a voltage in this material, so this 2D material, you can change by exploiting Stark effect, you can change the position of the exciton resonance that you have naturally in this material, right? And doing this, changing the position of the excitonic resonance as in relation to the wavelength that you are illuminating this metasurface, you change the imaginary part of the refractive index, and then you change the refractive index in the end, and then you can also then change the way you're focusing light with this kind of advanced Fresnel lens, although it's not exactly a Fresnel lens. You can also exploit the electric current in order to manipulate the response of a metasurface. In this case, the metasurface is simply this spiral of, this is an electric trail, just it's an electric path, right? So you apply a voltage and you create a current. And this guy here, this metaatom, is covered with a polymer. Then, when you pass current to this metaatom, you generate heat through Joule effect. This creates a temperature gradient inside this polymer, and the polymer has a thermo-optical response. This then changes the refractive index of this polymer, and then this polymer acts as a lens with different and dynamical properties, right? In this case, you can change the shape of this metaatom. So you see here that the metaatom has a broader, this path here is broader in this region. This means that here the current will be smaller than in the edges, for example. And depending on how you design this, you will have a different temperature gradient in your polymer, and this will reflect to a different refractive index profile also inside the polymer, right? And then the sky is also the limit. You can, for example, shape this wavefront like this. This means that you're producing a convergent lens, right? You could also generate other kinds of behaviors for the wavefront. So you can control the wavefront at will, and for example, you can easily control the focal length of this kind of material. So it's a lens with dynamically controllable focal length, right? And everything also in a flat world. Okay, there are also several platforms that can be used to endow metasurfaces with these tunable properties. For example, you can use graphene. You can put graphene upon a metasurface. We know that when we apply a voltage in graphene, we can change the Fermi level, right? And this means that depending on the wavelength that you're using to illuminate the sample, depending on the voltage that you apply to the graphene sheet, you can block or you can allow the absorption of light. So this means also that you're changing the response of the metasurface. You can use also transition metal chalcogenides as well. You can use liquid crystals. In this case, by applying a voltage, you can orient the molecules, the liquid crystal molecules, and then you can tune also the amount of matter that light is seen when passing through this metasurface. So you're also changing the effective refractive index of this material. So you can also control with this the degree of interaction between light and matter. Also using conductive oxides, you can do many things, but all these platforms, they suffer from relatively poor switching contrast, or they make the integration in devices or systems a little bit difficult. And then the phase change materials, they come into play, right? Normally these phase change materials can undergo a phase transition of a low temperature type and high temperature type. Normally you associate the low temperature with an insulating phase and the high temperature as a conductive phase, right? And these changes can be very large, allowing large switching contrasts. Two main actors play the role in this phase change materials community. One is the germanium antimony telluride, so the GST, which is a non-volatile phase change material. This means that when you induce the phase change, when this external stimulus is gone, the material stays in the changed phase, right? On the other hand, the vanadium dioxide is a volatile phase change material, and this means that you have on your external stimulus, and then you induce the phase change, and as soon as the external stimulus is gone, the material comes back to the original state, so the previous phase. So this is, of course, both of them are important, but in the case of tunability, of providing tunability to metasurfaces, vanadium dioxide is more interesting, and this is why we'll focus on its properties. So please, Stefan, tell me when I have 50 minutes left.
Yeah,
50 minutes left.
15.
No, 50. Yeah? Okay. So, thank you. Yes. In the case of vanadium dioxide, what we have, so this material has very interesting particular properties. First of all, the critical temperature is very low for phase change materials in general. It's about 70 degrees Celsius. And below this temperature, what we have is a monoclinic insulator. Sorry for this expression here. It will be clear very shortly why this is a misleading expression. And in this case, we have this kind of structure. And then during the phase transition, this is under debate to explain exactly the phase transition mechanism of vanadium dioxide, but it's more or less agreed that we are speaking about a strongly correlated metal, but above the critical temperature, it's a rutile metal, so it's a structure like this. So it's a structural change that vanadium dioxide presents when performing the phase change. This phase change presents a small thermal, sorry for this, here this is an H here, thermal hysteresis. So this means that when we increase the temperature, we get this, so we get this hysteresis curve here, and this is a very, very thin hysteresis cycle, which is important in many applications. Also an important characteristic is that this system survives by millions of cycles. So if you make if you cross this transition point millions of times, the system keeps on behaving as if time hasn't gone by. And finally, which is important for the applications, optical applications, is the very large refractive index change when we cross the phase transition, right? So in this case, you can achieve up to 1 refractive index unit when inducing the phase transition in vanadium dioxide. Questions, comments? No? Yeah? It's not possible. Yeah? Okay. Very good. Okay, then let's now put everything together. We would like to have a tunable metasurface working in the visible range. I hope you have realized that many of these previous applications, they happen in the middle, so the near infrared and so middle infrared. We would like to work in the visible, right? And in order to understand how we can bring this functionality to metasurfaces, let's study first the properties of single vanadium dioxide disks, nanodisks, and then we will see what changes when we put many disks together to form a metasurface. Okay, so here I show you to the left and in the middle panels the simulated extinction or scattering spectrum of single vanadium dioxide disks, and these dimensions here are realistic dimensions, so close to what we were going to implement experimentally. So they are 200 nanometers high, and so they are disks with diameters varying from 100 nanometers to 300 nanometers. What can we see here in the left panel? This is the scattering in the low temperature phase, so at a temperature of 30 degrees Celsius. Here we have the scattering cross-section at high temperature, so 90 degrees Celsius. So in this case of the low temperature phase and the high temperature phase, I will avoid using the insulating and metallic phases. And this will be clear in a moment. And here to the right, I present you the experimental results of ellipsometry in these two materials at low temperature and high temperature. So ellipsometry is a technique that allows us to measure the real and imaginary parts of the refractive index. So in this case, the real part of the refractive index is this continuous line here. Continuous line, solid line blue is the real part of the refractive index in the low temperature phase. Continuous solid line in the red is real part of the refractive index in the high temperature phase, and the dashed lines correspondingly the imaginary parts. Very good. What can we see here from these two graphs? So we see here that in the visible, we have, for both low temperature and high temperature phases, we have a set of very strong resonances, which, of course, so the scattering increases as the size of the particle increases. This is clear, right? So larger particles scatter more light than smaller particles. And we see here that as the size of the disks increase, we see that there is a red shift of this resonance here. So this resonance is the Mi-electric dipole resonance induced in these disks, in these individual disks. And as the disks get larger and larger, they start emitting also a Mi-electric quadrupole resonance. So these resonances that in principle occupy more space starts fitting inside the particle, and then they appear. But you see that this also happens in the high temperature phase. Back to the near infrared now here. In the low temperature phase, we don't see any kind of resonance, any kind of Mi resonance. This is simply because for these wavelengths here, these particles are still too small to accommodate any kind of Mi resonance, right? But you see that, on the other hand, in the high temperature phase, there is a resonance appearing, right? And this resonance is a plasmonic resonance. It has a plasmonic characteristic and not a Mi resonance. And why is this? It's because, as you can see here to the right, at this high temperature phase, the real part of the refractive index from 950 nanometers on gets negative. And this is what characterizes the behavior of a metal, right? It's the negative real part of the refractive index. And as so, you can talk about plasmons, right? So in this case, particles with these typical sizes, they present plasmonic resonances at these wavelengths. And then, now I think it's clear why it's misleading to say insulating or metallic phases, because you can tell this, you can use this kind of nomenclature of these expressions if you're talking about the infrared, the near infrared. Because in fact, here in the near infrared, this material is dielectric, and at low temperature and at high temperature is metallic. But in the visible, the real part of the refractive index is always positive. So in the visible, this material is always dielectric. So you cannot say that vanadium dioxide is metallic above the critical temperature and isolating or dielectric below this critical temperature. Okay, so let's then talk about our experimental results. Again, we fabricated by electron beam lithography. So it's writing on a surface with an electron beam. It's very fun. 200 nanometer high nanodiscs with diameters varying from 140 to 290 nanometers. So this is the scanning electron microscope of the structures fabricated. You see that the discs, they present a considerable roughness along the perimeter, right? But it's the best one can do. This is a tricky material to work with. And now we also investigated the optical properties of these disks. And in order to do this, we performed the so-called dark field microscopy or dark field spectroscopy, which is a very smart technique when you want to record or to scattering from particles. So scattering from nanoparticles is always very weak. This means that you have to try to suppress your background as much as you can, right? And one way of doing this is simply shining light on the sample in a glazing angle, right? So that the illumination light gets reflected in this direction, and it's not collected by the collection optics. Only the light scattered by the particles, which is wavelength selective, will be collected by the optics and sent to the spectrometer, right? This is fantastic. When I was a student and I got aware of this technique, I was completely fascinated, right? It's very smart, very clever. And the idea is very simple. And this is what we get. Here, you see the spectra, the dark field spectra of each of these disks, starting from the smallest disks to the largest ones in the low temperature phase, the high temperature phase. And you see here the images. So the dark field images from the smallest field, you see here a little bit bluish, right? This is what we see in the microscope. If you look at it, right, it's a little bit bluish. And in fact, you see here that the smallest disks, they peak, the scattering peaks here close to the bluish greenish, 500 nanometers or so, 510. This is turquoise, right, color. And then you pass to an orange guy here, right, which is a little bit larger. You see here you are already at 600 nanometers or so, the orange, reddish. It's nice. So this is what we get. And we see, by the way, these are indivisible. So both materials are being investigated. So both phases investigate indivisible. And then this is how these materials behave when you're investigating single nanodisks. And now, what happens when we make a metasurface from these disks? So in this case, again, so I'm showing here only the simulations, FDTD simulations of the response of single nanodisks and an array of 13 times 13 disks. This number is like it is 13 by 13 because we saw that if we increase the size of this array, the response, the spectra, they did not change very much. So we stop it there with a smaller metasurface because then the computational time is shorter. Okay, so what can we see here comparing these two behaviors? The first thing is that, of course, in the array, the extinction cross-section is much larger. Of course, because instead of having one disk, we have now 13 by 13 disks helping in scattering light, so it's much more effective, the interaction with light. Besides this, we see also that these resonances, right, so these mini-resonances, they get narrower in the metasurface. And this is because with this, so so each one of these disks, they act as an antenna, right? And this is a common and well-known effect. So if you have a microwave antenna on a tower, right, outside on the field, these antenna will irradiate a dipole emission pattern. But if you put many of these antennas side by side, the constructive and destructive interferences will happen in space, and then you can get a much, for example, narrower emission, right? The same thing happens here. And since you have a much narrower spatial emission, you are more or less limiting the decay channels, the loss channels of these antennas. And this is, and less losses, smaller losses, implies narrower resonances. And this is why the resonances, they get sharper when you put these disks on an array. Okay, now I think we are ready for talking about tuning, switching, temperature switching, right? And this is what we get. Again, I'm getting the same results as I showed before. And I define as a figure of merit the modulation depth, which is the logarithm of the scattered intensity in the low temperature phase divided by the high temperature phase. And when we plot this, just taking this data from these two graphs, and we plot for the single nanoparticle and for the array, the first thing we have already saw, so both aspects we commented can be seen here also. And they are, first of all, the narrowing of the response in the array as compared with the single disk, and also the enhancement of the modulation depth in the array, so it's larger than for a single nanoparticle, single nanodisk. Very nice. And in fact, we can reach modulation depths of 2.6 dB when we use an array like this, which is, by the way, a very good result because it's really challenging to achieve such modulation depths using phase change materials and tunable metasurfaces in general, right? Our experiment, so these are simulations, right? Our experimental results are here. So we just make this experiment and then we calculate the modulation, we measure the modulation depth as a function of wavelength for disks with varying diameter. So this is a small disk, this is a larger disk. And what do we see? We see that the modulation depth depends on the nanodisk size. So this is clearly shown here. And and by the way, also for disks with different sizes, these modulation depths in a very decent spectral range here, the modulation depth is very large, 2.5 dBs. And this is, of course, very important because this can allow us to design metasurfaces with spatially varying modulation depths. So if I fabricate a metasurface not with disks of all of the same sizes, but if we encode sizes in space, we can achieve something that similar to what I showed you in this biosensor, in the pixelated metasurface for detecting molecules. But here, the applications may be different. I will come to this in a while. Okay, it's already 2:45. Although I still have 40 minutes, I think I will stop here, right? So what we have shown here, so we fabricated and systematically studied the single and arrays of vanadium dioxide nanodisks. Previous works in literature showed always exploited the phase transition on the plasmonic band, so also always exploited tunability or modulation using that plasmonic band, exploiting the fact that at low temperature the plasmonic band is not there, but at high temperature the plasmonic band is there. In this talk we focused the studies in the visible range, which is evidently important because it's our world, right? We also showed that these metasurfaces can be quantitatively tuned with very good for the state-of-art modulation depths. This means how much the scatter changes in both phases, low temperature and high temperature. And also we showed in the very end that these modulation depths, they depend on the sizes, and this means that they will also be different for different wavelengths because the size of the particle is related to the Mie resonance and everything is based on the Mie response of these disks. And this can be, for example, used to encode different modulation depths in space, which can be used, for example, for implementing anti-counterfeiting strategies, because then, so if you have some material that can be heated up to 70 degrees or so, you can just record or print a metasurface with these guys at a given position, and then you know that the disk in the position, the first row, the third column is responding at this wavelength and so on. So if someone changes these materials, if someone changes this product or device, you will know, because only you know where you put your nanodisk with which size and so on. Okay, so that's it. I thank you very much for your attention, and I'm happy to answer questions. Thank you.
Okay, thanks a lot, Leo, for this nice introduction to metasurfaces to our audience and showing some of your work. Any questions? Yeah, Amanda?
A really simple question. Are they easy to make, the nanosurfaces?
Yeah, so it depends. I showed many different strategies. So the direct laser writing, for example, is very simple. It's a polymer, it's a closed machine, although you can do it by yourself. You can also build such a setup. But it's everything automatized. In this case, it's tricky because to nanostructure this material in particular is very complicated. The same thing happens with gallium phosphide. But there are other materials which are extremely easy to deal with, like titanium dioxide or silicon. So this depends on the materials that you have and also the limits that you want to achieve. If your application is very critical against fabrication imperfections, which are always there, then you have to sweat a little bit more in order to achieve a good device. So this depends on material, application, and so on. Yeah.
The natural occurrence of vanadium in nature is vanadium pentoxide, which is stable up to 1,000. So how do you produce vanadium, which is so important for you, the dioxide? And when you speak of its volatility, you're not referring to a liquid phase, it's a transition.
Yes, I also ask myself these questions.
Yes.
Yes, because vanadium dioxide, in fact, can assume 5 different oxidation states, right? And one in fact, the most important problem in this system is to control the valence of vanadium dioxide. And I'm not a fabrication guy. This is the role played by our collaborators in the Technical University of Brno in the Czech Republic. And they are specialists in vanadium dioxide. So since the beginning of the universe, they are dealing with it. So they know how to deal with it. But I completely agree with you, and I know this, that this is a critical point. It's very complicated, yeah. Yeah, but how they control this, I don't know, but they have the know-how how to deal with this.
I think it's a laser. Is it a laser ablation?
No. Yeah, it's deposition, but it's not laser ablation, because with the laser ablation, it's yes, you have to fabricate in a very slow process, because if your fabrication is very abrupt or something like this, then you don't have control, right? And then you generate all the valence states, and then you have heterogeneous film, and not only in the valence state point of view, but also in the roughness point of view. So you have to deposit very slowly, right, to keep controlling the stoichiometry of the materials that you're depositing, and also to keep the film as smooth as possible, right? Because you also don't want to have scattering due to surface roughnesses. You want to have scattering because due to the Mie resonances, and not because the particle is rough. Yeah? Yeah.
So when you had the slit and you were showing the second harmonic generation and stuff, it was clear to me that the slit gave you like an orthogonal dipole mode and some magnetic mode.
Yeah.
But it wasn't clear to me why that led to like non-linearity.
Yeah, it's because, in fact, perhaps I haven't stressed this. Thank you for your question. So when you shine light here, so you have, it's like, so you can have a charge accumulation here, and this is as if you had a condenser, a parallel plate condenser, but with 2 plates which are very close to each other. So the field enhancement there is very large, right? Electrostatic in this sense, right? And then you exponentiate any kind, so you enhance any kind of nonlinear effect abruptly because they are nonlinear, right? Yeah.
I was just curious, so you talked about making things cheaper and flatter and smaller and this kind of thing, but is there ever a purpose in metasurfaces of making things just better? So for example, just in conventional optics, a big mirror, for example, a telescope, many of us are astronomers. Is there any use in making your surface bumpy like this in some controlled way?
Yeah, I don't know. I think that, okay, so you mentioned explicitly the telescope. I'm not an astronomer, but I imagine that for a telescope, if you want to have a large resolution, you have to have a large numeric aperture. So you have to go to very large lenses if you're dealing with refractive optics. If you're dealing with reflective optics, you also need a huge amount of aperture in order to collect as much light as you can. I don't see a great advantage in this case, because this application is intrinsically a macroscopic application, right? So I think that nobody nowadays uses professionally refractive microscope because of the chromatic aberrations and so on. So, but then if you're talking about a mobile phone, right? And then, so this can start, it can start being interesting to use flat optics, or if you want to produce a ultra compact endoscope, because so if you want to make a stomach examination, so you have this tube inside of you. So if you could have a tube which is an optical fiber, and only this would be much more pleasant. You wouldn't need perhaps to take some anesthesia. By the way, I liked it because it's a way of legally get a little bit away from this planet. But this perhaps is not the case of everybody. Huh?
What I'm really asking is whether you can beat the diffraction limit with a conventional mirror.
No, I don't think so. With a mirror, I don't think so. As soon as you have propagation, you cannot beat the diffraction limit. In order to get an optical resolution better than the diffraction limit, you have to have access to large spatial frequency components, and these components are all inside the near field. So you have to access the near field of an optical source or an object in order to break the diffraction limit, optically speaking. So there is no way of breaking the diffraction limit, I think.
Yeah. Can I just add to this, because
yeah.
Like you said at the beginning, can we make something better? So one example of where you can make something better is what Leo mentioned at the end. You can get a very large numerical aperture. So for example, with a single optical fiber, it's not possible to make an optical trap. So in biosensing, biospectroscopy, often you want to trap, I don't know, a microbead that has some molecules on it in a liquid, and you can do this with a high NA objective. So it's not possible to do that with a fiber, no matter how good you make the ball lens on it. But with a metasurface fiber, it is. Because if you do something similar what Leo shows there, but you design it a little bit different, you can actually get into the NA region that you just need to trap a silica sphere, for example, in water. Yeah, so that's one example. But competing with real optics, that's challenging. So there are two companies in the US that I think one is working with Zeiss, the other one I don't know with whom now, that I actually try to see can we get metasurfaces that will actually replace your normal lenses in microscopes. Yeah, but that's not.
Sorry, it's a comment on the comment.
Yeah.
This is a reality already, right? So this is not being used commercially, but so now optical tweezing is something this size. So you don't need bulky objectives and so on. You can just use this kind of approach, and this has been done already. So including multiple tweezing spots, right? Because the response of this metasurface depends on the state of the incoming light, and then manipulate the state of the incoming light. You can choose to focus here and there, or here and there and everywhere, here, there, and everywhere. This is Beatles, right? Here, there, and everywhere. Someone would ask a question there, over there? Yeah, so, sorry.
Yeah, maybe a follow-up to what Daniel was asking. With these kinds of flat optics, is there any kinds of aberrations that you incorporate in general as part of the fabrication process?
This aberration, you mean in the optical response? Yeah, this is something that you can aim at, and this is what has been done here. So as I understood your question, so in this case, this metasurface was designed in order to present a focal distance which is within 400 nanometers in the near infrared, invariant. So I think that as far as I know, the normal achromat bulky lenses that we have in the labs, they don't perform so well as this kind of metasurfaces. And then something that you can ask is, okay, this is near infrared, but what if what about the response in the visible? And then we start having a problem, but it's a technological problem, which is the fact that we don't have spatial resolution enough in the fabrication, because if you go to the visible, you have to perform, so these structures here, these individual structures, they have to be scaled down. And these starts approaching our resolution limits in order to fabricate them. But this is something that can be circumvented, and someday, so the frontiers of the technologies are being pushed constantly, right, to better regions. But this is an application in this direction. So you can design a metasurface to have an achromatic behavior.
Yes, but I guess I was asking more about unintentional aberrations. Like, you know, when you have a sort of typical glass lens, like essentially it's your machining precision that introduces a lot of different aberrations. And I'm wondering if the fabrication of these arrays presents opportunities for incorporating other kinds of aberrations.
I don't know if I understood your question, but I'd like to, I would tend to say yes. So because the sky is the limit for this stuff, right? So you can incorporate so many functionalities at the same time. You know, I don't know if you're asking about unintended, so fabrication defects. Yeah, and that, yes, but this is, I think that something that happens in any fabrication strategy. You never make everything right from the beginning. So you do this, I think this was also the case in this particular study. So the first fabrication did not lead to a nice result, and then you have to iterate this until you get to the recipe. But yes, I don't know if I answer your question. Okay.
I guess one of the things is like the better your fabrication, so the smaller you can make it, right, the more all of this acts as a point scatter, right? And then it doesn't matter so much anymore if it's, I don't know, if it's knobby or if it has a surface roughness or so, right? Because like all of what you do is you like change the local phases, right? Like as you said, like you change the Huygens phase profile. And if everything is really a point scatterer, then fabrication inaccuracies don't matter so much anymore. So if you have very good resolution compared to the size of the wavelength, then I think the answer is there's promise. If you are at the limit, you know, like a third of the wavelength, a fifth of the wavelength or so, then you need a really good fabrication, otherwise you have issues.
Ulrich. Yes, so sorry if this question is not quite incorrectly, but in particle physics, we have a lot of detectors now where we want to detect single photons effectively, and we're now moving to a large extent to use silicon photons for that. So they are microscopic, they have tiny, tiny wells that the photons get into. But one of the problems we have is that the photons actually have to come in with a quite high incidence angle for them to be detectable. And people have then tried to basically do, you know, not microscopic at this level, but basically put tiny lenses on top of it.
Micro lenses, yeah.
Could this potentially replace that?
I think so.
Put like a flat surface on top of it,
so.
and where you didn't need to have an alignment problem.
No, I don't think so. And you're talking about visible photons, right?
Yes, visible.
Yeah, yes. I think this is the future. So this to replace micro lenses, mainly micro lenses. So this.
Just quickly, vanadium oxide. My understanding is that the phase transition is really structural, and that's concomitant with the change in the electronic band structure.
Yeah.
But now you mentioned that your material was metallic in the visible, and near, oh no, the other way around, insulating in the visible.
Yes.
And in the near infrared, your dielectric constant was negative.
Exactly. Yes. In the infrared, you can talk about metallic and dielectric transition phase.
But
transition.
electronically, let's forget about wavelengths. What's
You mean in terms of transfer?
instead of band structure?
Oh yeah. So yeah, I'm not a yeah 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 yeah. I'm not a specialist in this, but I would say I think there's still a gap. There's still a gap, but then there is electronic promotion to this conduction band, to thermal promotion of these electrons, and then you have a given mobility of charges. Yes, but I don't know. So these I don't know exactly. These things about the phase transition itself of VO2 is still a matter of debate. You can also induce phase transition in a ultra-fast manner, right? So this phase transition may happen only in ultra-fast regime. So if you shine an ultra-fast light pulse, and then after the pulse is gone, the system is already in the dielectric, so to say, phase. This means that this is a purely electronic change in the material, so there is no time for the lattice to change. So it's complicated. I cannot give you a nice and correct answer. Yeah.
Okay, so let us thank Leo again.
Thank you.